Let's see if we can figure out how to differentiate an inverse trig function. And how I want to start this is by looking at the graphs. So here, this first one is the graph of arctan. Now, one of the things I want to point out about this graph is that it is always increasing. Yep, look at that, always increasing. So we would expect the derivative of arctan to always be positive. Now let's look at arc sine. Now here's arc sine. Notice it's always increasing. All over its domain, it's always increasing. That's arc sine. And then we'll look at arc secant. Arc secant, here it is. Notice that arc secant is also always increasing. Always increasing. So what we get from this right away is we expect the derivative of arctan, the derivative of arcsecant, and derivative of arcsine to all be positive. We want them to be positive always. Now let's look at the cofunctions. Let's look at cotangent. This is the arc cotangent. And you can see it's always decreasing. Moving from left to right, we're always decreasing. Let's look at arc cosine. Once again, always decreasing. From left to right, always. And finally, let's look at arc cosecant. And it too is always decreasing. So we notice this. All these cofunctions, all the arc cotangent, arc cosine, arc cosecant, all of those are going to be negative. They're always decreasing. So that's one thing that we note right away before we ever start trying to find the derivatives. We know kind of what we're looking for. So we'll start off looking at the derivative for arc tangent. Okay, so we want to find dy dx here. Well, here's the way I'll proceed. I'm going to apply tangent to both sides. So what I'm going to do is get tangent y equals x. Now, from there, we can implicitly differentiate. So I'm going to take the derivative of tangent, which is going to be secant squared, times the derivative of the inside, just y prime. And then the derivative of x, which is 1. So there's what we have. Okay. Now remember, what I'm trying to find is y prime. So let me go ahead and solve. I get 1 over secant squared y. So there it is. There's the derivative. There's dy dx, the derivative of arctan x. Now let's though go a step further and let's figure out what this secant squared y is. Now I want to go back to this thing right here where we have tangent y equals x. I want to make a little triangle. Okay, I'm going to make a little right triangle, and I'm going to call this angle y. And remember, tangent is opposite over adjacent. So this side here would be 1, and this opposite side is x. Using Pythagorean theorem then, well, what am I doing? Erasing. I had it right. This is just going to be 1 plus x squared. Yeah, like that. 1 plus x squared. So we know then that secant y is going to be hypotenuse over adjacent, like that. Remember how secant is hypotenuse over adjacent. So what about secant squared? Well, secant squared y would just be 1 plus x squared. Yeah, there it is. So we know that the derivative of arctan is going to be 1 over this right here, but this is 1 plus x squared. Yeah, there it is. So we've developed the derivative of arctan. We know how to find the derivative of arctan, and notice we said that arctan is the derivatives. The function is always increasing, and this is consistent with that because notice this is 1 over 1 plus x squared. This can't be positive. This can't be negative, right? You plug in any real number, you're going to get a positive number. So the derivative here is always positive. So let's look at some examples of how we would differentiate arctan. So let's suppose we have arctan of 5x, let's say. So we just go back to this formula here. We've got 1 over 1 plus, not x squared, but 5x squared. And we use the chain rule. We have to use the chain rule. So this is times 5, derivative of 5x. So what we have then is we have 5 over 1 plus 25x squared. There it is. So there's the derivative. So you see the chain rule is involved here, like usual. What we've done is we've just learned another technique, another function that we can differentiate. That's what we've learned here. Now we can do the same thing with sine. If we did the same thing with sine, so let's just go through this. We've got y equals arc sine of x. And I want to figure out what the derivative of that is. Well, we can proceed as we did before. I can apply sine to both sides, and I get sine y equals x. And then I can differentiate. The derivative of sine is cosine. And remember, we're using implicit differentiation here. So I tack on the y prime equals the derivative of x, which is 1. And then we have this. We have y prime is equal to 1 over cosine y. Now, like before, I need to figure out, well, what is cosine y in terms of x? So just going to draw a little triangle, a little right triangle. And I have y here. And remember that we're dealing with sine y equals x. And sine is opposite over hypotenuse. So using Pythagorean theorem, we would find that this is 1 minus x squared, the adjacent side. So now we have cosine y equals 1 minus x squared over the hypotenuse, right? Over 1. Yeah. So now we know what the derivative is. The derivative of arc cosine. Okay. The derivative of arc cosine is 1 over this cosine y. So this is going to be 1 over the square root of 1 minus x squared. There it is. So we have a formula here. Now we could use this. So let's suppose I want the derivative of arc cosine of, let's say, 7x plus 1. Okay, so here we go. I've got 1 over the square root of 1 minus, not x squared, but 7x plus 1 squared. Times the derivative of 7x plus 1, which is 7. So there we have it. And of course, you might want to write this as 7 over the square root of 1 minus 7x plus 1 squared. If you want, bring the 7 up top there. But anyway, there's the derivative, and you could expand that out, of course, but no need to for right now. That's how we find the derivative of arc cosine. Now I want to develop the derivative for inverse secant. Now, this is the graph, as you can see here, for inverse secant. Remember, I said that, the derivative is always going to be positive because this graph is always increasing here and increasing here. But look at the y values here. Let me show you here. Here is y equals pi over 2. And up here is pi. See? So notice this graph, this part of the graph over here goes from pi over 2 to pi. Now, that is the second quadrant. Yeah. So I'm going to refer to that later. But notice that is definitely the second quadrant. Y is in the second quadrant here. Now look over here on this side. When x is bigger than 1, we go from 0 to pi over 2. Well, that's definitely the first quadrant. So we've got a situation here, and I'm going to refer to this later, where y is in the first or second quadrant. So keep that in mind. So here we go. We've got the arc secant, and we want to figure out what the derivative is. So we go through all these steps, and you don't need to go through all these steps when you're differentiating an arc secant function. I'm just developing the formula for you. So what we have then is we have secant y equals x. Now, I want to differentiate implicitly. So on the left-hand side, we've got the derivative for secant, which is secant y tan y times y prime equals the derivative of x, which is 1. Okay, now I solve for y prime, and I get y prime is 1 over secant y tan y. Okay, there we have it, secant y tan y. Now, I need to go back and draw a triangle like always and figure out what secant y tan y is. Okay, so here's my right triangle, and I've got y here. Now remember, secant is going to be hypotenuse over adjacent. See? And then this over here then would be x squared minus 1, using Pythagorean theorem, the opposite side. Okay, so let's take a look here. We've got secant y equals, well, x. It's right there, right? No worries there. And then tangent y. Well, let's see what tangent y is. Tangent is opposite over adjacent, so this would be x squared minus 1. Okay, so if we plug in, here's what we've got. We've got 1 over x square root of x squared minus 1. There it is. Now, we got to be careful here, because notice there's a little bit of subtlety here. Remember, I said that y is going to be either in the first or the second quadrant. Now let's think about the situation then. If we're in the first quadrant, well, we've got a positive times a positive, right? Because secant is positive in that quadrant, and so is tangent. But what if we're in the second quadrant? What if y is in the second quadrant? Well, secant is 1 over cosine, and it's negative over there, and tangent is also negative. So a negative times a negative, well, that's also a positive. So we've got to take measures to make sure this is always positive. Plus, remember, the derivative is always positive for inverse secant. So here is what we're going to do. For arc secant, we're going to say this is 1 over absolute value of x. Because, you know, this square root of x squared minus 1, that's always going to be positive. So what we can do is put an absolute value around the x part. So here is the derivative of arc secant. Now, let me tie all of these together. We've looked at the derivative for tangent, sine, and secant. So remember, the derivative, the first one we looked at was tangent, but let me just go this way. I'm going to do sine. Whoops. I've been using arc sine. So let me, okay, so we've got arc sine. And remember, that's 1 over the square root of 1 minus x squared. we've got the derivative of tangent, arctan that is, and we said that's 1 over 1 plus x squared. And then we've got the derivative of arc secant. And remember, all the other differentiation rules are still at play here. The chain rule, the quotient rule, the product rule, but these are the formulas for these standalone functions. Remember, this is absolute value of x, square root of x squared minus 1. Now here's the thing. These are the ones I found. You could go through a similar process and you could find the derivative for arc cosine. It's going to be just like arc sine, except it's going to be negative. It's always negative. There it is. Likewise, arc cotangent. So arc cotangent is going to be just like tangent, arc tangent, but negative. See? So this is an easy way to remember them. And then likewise, the derivative of arc cosecant is going to be the negative, right? Like this. Yeah, so if you remember these three, then you can remember the cofunctions over here because they're just the negative of it.